right, so remember when we looked at a position time graph, we spoke about the gradient of a velocity time. We spoke about the gradient of a position time graph. It's important to realize that it was the position versus time graph and that it means velocity. So whatever the gradient does, that's what the velocity is doing. So that's what we looked at yesterday. So, admit. Okay. I wonder if it would be bigger if I did that. No, it's the same. Is it? Is it bigger the other way? Is that better? Okay. I don't know what I just did now. Okay. All right. So let's go to page 2 and let's fill this out. Okay, so let's just see what happens here now. So yesterday, I had my little piece of paper that indicates a straight line. Sorry, it got a bit graunched in my pencil bag now. Okay, and you can see how the gradient, and let me draw it here. So I'm going to draw, please, this is the only time I'm allowing you to do notes with a highlighter. You never touch a graph with a highlighter. Please, please, please. Okay, so I'm going to draw it. So there you can see a gradient, okay, and it is 0. And we know that it started from rest, okay, because the gradient is 0. That means the velocity is 0. And as we go, let's remember, I'm just touching it with that one little point. You can see now, oopsie, how the gradient changes. Okay, and we can see at this point, we are seeing how steep the gradient is. So you can see how the gradient keeps increasing. Oops. Gradient increases. Okay. Oh no, now what? Okay. All right. Gradient keeps increasing. You can see that because we're going from a 0 gradient to steep to steeper. Okay, so that's what we are looking at. And that means that the value of the gradient actually increases. So because the gradient increases of a position versus time graph, okay, you've got to make sure that you're looking at a position versus time graph. That means that this gradient is the velocity, and the velocity is increasing then. Okay, I want you to remember, sorry, my pencil's going down. Okay, I want you to remember this relationship. Okay, so now let's take a look at how would we draw a velocity time graph. So I want you to prepare yourselves now. We are moving away from a position time graph, and a position time graph is very, very special. I'm going to show you just now what else is special about a position time graph, okay? But mentally, you are preparing yourself to move to a velocity time graph. Why is this sorry girls, the projector at school keeps switching off. So I'm just trying to get it working again for the girls here. It's very loose, this thing. Okay. So let's take a look. We know that the velocity starts at 0. The velocity is 0. And we can see that it increases. So if we had to do now a velocity time graph, please girls remember that the graph, the actual graph here is the position time graph. Okay? I'm showing you how my position is changing over time. But I'm talking now about the gradient of this line. So the actual line is how the displacement is being changed, but the gradient of the line is the velocity. Okay, does that make sense? Is it clearer? So the actual line, so if I was to go, oh, what is that? Oh, it's 18 meters. The readings on the graph are position, but the gradient of the graph is then velocity. Okay, please make sure you realize this. So now we are going to go and look at how would a velocity time graph look like this. Now, it is a constant increase of velocity, okay, because it's a constant increase of the gradient. So now let's start at the beginning. Can you see that it starts at 0 velocity? So that means it has to start there. It starts at 0. And it increases the velocity. And I'm going to tell you right now, velocity time graph will never have a curve. Only straight lines. Whether they're horizontal or diagonal, they are only straight lines, okay? So velocity time graphs will never have a curve. Position time graphs do have curves, okay? So knowing that, and knowing that it slowly increases, we can then draw a straight line increasing the velocity. Does that make sense? Yeah. So just let's think about it. Okay. I start at 0. The gradient is 0. We have a bigger gradient, which means we have a bigger velocity. The gradient keeps increasing. The velocity keeps increasing. Look how my velocity keeps increasing as we move over time. Okay, so there is the corresponding velocity time graph. So I've basically plotted the gradient, how the gradient is changing of a position time graph. Okay, now, is there an acceleration? There is an acceleration. Remember, in your head, what you must say is when I say acceleration, you must go, is it going faster, 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 slower, 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 or is it changing direction? Okay, so it's going faster, faster, faster. We already said that at the top. So we know there's acceleration. Okay, but I'm now going to tell you another trick about acceleration, is that acceleration time graphs only ever have horizontal lines. So it makes it a bit easier. So we know we are accelerating, and we can say that we are accelerating in the positive direction because look at my gradient of my velocity time graph. Remember, the gradient now of this graph gives you acceleration. So it's a positive gradient, so it means I get a positive acceleration. But look at the gradient. The gradient of the velocity time graph is constant. And so my acceleration is constant. I'm not sure yet what it is. We haven't done calculations yet, but I know that that's what it would look like. Okay, any questions on this? Think about, remember the velocity is increasing, but look at the gradient. Can you see the gradient is just the same everywhere? It hasn't changed. Whereas look at the gradient over here. It goes from 0 and then it changes all the time. So can you see the difference? So a curve's gradient can increase or decrease, okay? But a diagonal straight line, no matter where you take the values to do a reading or it will give you the same gradient over and over. Okay, and then how would I, okay, a negative acceleration. Let me just finish reading the question. It popped up and then it went down. Okay, so a negative acceleration, you see if you've got a 0 line over here, it will carry on going down, so you will have a negative side. So Homo has asked, how would a negative acceleration look like? So if you've got the x-axis here, then it would land up being underneath the x-axis. So that would be a negative acceleration, where this would then be a positive acceleration. Okay, and can you remember what are the what's the word I'm looking for? What are the factors that will give you a positive acceleration? If it's going in a positive direction and going faster and faster, or if it's going in the negative direction and going slower, slower. Okay, remember, if you're going negative direction, but it's a negative acceleration, so it's going slower, slower, it's going to land up on the positive side. Okay, just like in maths. Okay, right, so officially we are going to start graphs. This was a little before we start worksheets. Okay, now what I want you to do is I'm going to, in every single exam in matric, so the physics and the chemistry, they give you a graph to plot. It's a very big thing to do. That's why I did those graphs at the beginning of the year. Okay, graphs are very important, and choosing an appropriate scale is very important. You know what they do sometimes? Sometimes they leave the scale for you to fill in. You've got to realize what the scale is, and that could be quite hard. So, or difficult, I should say. So I want you to now start practicing how to do your scales with this. But majority of the time, we want sketch graphs. Okay, but for now, we're going to do plotting so that you can see what happens. So girls, I'd like you to start plotting this. Let's just take a look at the values. So our position is going to go up, and then can you see that it starts coming down? I'm going to tell you now that there are curves here. Okay, so I'm going to draw this with you. And you can see they are all on the positive side, so it's really fine. We don't have to divide this graph paper into two. So we only need the one quadrant for it. Okay, so we're going to do a position. I need a lead. Oh, I've run out of lead. Sorry? I've got lead. It's okay. Thank you. But I appreciate that. I'm just going to add lead. Oh, this isn't even open. Oh, won't be long. Oh, they tell you to twist. Oh, that's clever. Always read the instructions. Okay, but now I'm still not opening this. Oh, there's a hole on the side. That's smart. I don't know when last I actually put lead in something. And I only ever use colored pencils. Ooh. Yeah. Right, sorry, I'm just putting lead in my pencil. Very fancy. I'm just going to throw a whole lot in there. Okay. All right, so let's see. Time is on the x-axis. Okay, and you can make it just a T with an S. Position, we can look at an X with a meter. So it's always in meters, always in seconds. Okay, we know we're going to start at 0. Make sure that you always indicate your origin. And let's see, what are we going to go up in? We need 14 for time. So let's see, 1, 2, 3, 4, 5, 6. Ugh, I've only got 6. How are we going to do this? 5s, 5, 10, 15. Fives are not nice at all. Why would I do that? You see, you're not supposed to. That's the thing. I know you guys do that. You're not supposed to add another thing. You must use what you've got. 2, 3, 4, 5, 6. I don't want to go up in threes. Threes are not nice. And neither are fours. Almost want to say to you, let's do it. Why would I do that? Yeah. 3, 6, 9, 12. See, threes are really bad because how are you going to plot? Let's see, can we make it? Let's make it so that does it work if we make this a 4? Because the thing is, we've got even numbers. So if we go up in twos, that's the best way to do it. And we don't have to be on this line to do it. Because we're not going to plot anything else. So what if we take every fourth line and let's make that a 2? Does that work? 1, 2, 3, 4. 4, 8, 10. I forgot 6. Okay, I think it will. Every fourth line from the first line here. So 1, 2, 3, 4. There's 2. 1, 2, 3, 4. There's 4. 6, and we can go up in twos then. Here we go. And that has made it, oh, look what I did. Between my 6 and my 8. I think because I'm at an angle here. There we go. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 10, 12, 14. Okay, everybody, okay. Right, let's see. Now we need to go, what is our highest number that we go up on our positions? 5. 1, 2, 3, 4, 5. Yay, we can just go up in ones. 1, 2, 3, 4, 5. Okay, our highest is 5, so we go up 5s. All right, now we just plot. So, okay, now remember, because this is 1, and in these little ones, there are 5 of them, that means that each one is going to be a 2. So it goes up 0, 2, 0, 4, 0, 6, 0, 8. So here is our 2 and 0, 8. Everybody okay? Don't forget that you also have a 0, 0. Okay, 4 and 1.7. So 4 is over here somewhere. So remember, this is 1.2, 1.4, 1.6, 1.8. So it's halfway through that one. Okay, a nice little dot with a cross. Okay, 6 and 2.5 is 2, 2.2, 2.4, 2.5. Am I right? Please just double check that I'm okay. 8 and 3.4. So we know we're going to go up. Is 3, 3.2, 3.4. 10 to 4. Okay, 12 to 5. 14. Okay, so this is clearly a straight line. Okay, are you happy with that? There's no curve here. I'm quite happy that this is a straight line going up and then a straight line going down. Okay, so we don't, in position time graphs, we don't consider this as an outlier over here. Okay, we actually just connect the dots here. Okay, for this particular one, you will know when you see something that's, especially because this was not an outlier in terms of the way it was put. It was actually the next second that went like that. So it would be different if that was, it would be very different if this value here was at like 12 seconds and then 5 was 4, then that would be very different. But because it came after the 5, we can then draw it like that. Okay, I'll just wait for everybody. Okay, everybody there? Okay, so let's consider. Now, I'm going to tell you something else important about a position time graph. A position time graph has a very special line, okay? And a position time graph is specifically about where you are in relation to your frame of reference, okay, or your point of reference. I'm going to say it again. The position time graph. So when you see position time graph, your instinct must be already frame of reference. Okay. And the frame of reference is going to be where the x-axis is. Okay. That is your frame of reference. Okay. Frame of reference. Position time graph, frame of reference. They must just go together as naturally as possible. Okay, so the pink on here is just for a note. You never ever use highlighter normally on a graph, but we're okay for here because we are making notes. What I also want to remind you is that if you are doing a graph in a test, you may use pencil. The entire thing can be out of pencil. Okay, even in matric. Okay, so you can do your labels in pencil, your scale in pencil, your graph in pencil, everything it can be in pencil. All right, so if we consider the x-axis as the frame of reference. Now, girls, we're not saying that we are moving the frame of reference. It's just that we are spreading the frame of reference over time. Okay, now I want you to imagine as well. Remember I said to you, when you have a frame of reference, you put yourself at that frame of reference. So I want you to imagine that you are standing there and you are watching something making this motion. Okay, so this is now going to be relative to you. Okay, relative to you. And I'm going to tell you now that it is either a left or right motion or an up or down motion. We're not going to do diagonal motion. Okay, the only reason why this is at a diagonal is we have shifted a line so that it covers it over time. We have pulled it over time, and that's why it lands up being a diagonal. Okay, but so this is our frame of reference. So whatever is moving away from you. Okay, so it is going away from you in that direction. Don't consider direction on a graph. A graph is not a Cartesian, or it is a Cartesian plane. It is not a force diagram. Okay, it is not a vector diagram. It is a graph. You can't tell direction by looking at the line. I'm going to tell you now how you're going to tell direction by looking at the graph. Okay. So please, this is not, and in fact, I once set a question in a prelim paper where it was a position time graph, and I said to them, why can we not use this line to determine the direction? And that's because this is not a vector diagram, it is a graph. Okay, so what's actually happening is that the motion is just moving away from it, and you can say whether it is, if it's positive or negative. I'm going to say that, let's say this, you are staring at it, imagine you are looking and the thing is actually moving to the left of you. Okay, there's your frame of reference. Anything going in that direction would be to the right. Okay, makes sense. So imagine you are looking, it's not going up or down, because remember this is horizontal motion. So you are standing there, anything on the side is going to be moving left, anything on this side is going to be moving right. Okay, again, I have chosen left as positive. If you choose right as positive, it would be flipped over. Okay, so if I am looking at it left, it's positive on my positive side, and that's why it's going positive all the way. So let's consider. It's moving away. Can you see how it's moving away? Moving away, moving away, moving away. What happens here? It moved back towards. But can you see that we are still on this side of your frame of reference? Okay, so it is moving away. Now describe the velocity of it. Look at the gradient. Is it a constant gradient? It is, yes. We're going to break this motion up a little bit. Yeah, it is moving away and it's going at a constant velocity. Why? Because the gradient is constant. Remember, we are working on a position versus time graph. So we can see how it's moving away from the frame of reference. Your x-axis is always the frame of reference. You can literally see how it's moving away from it. Look at your changing position from your frame of reference. It was 5 meters away from your frame of reference. Here it was, what was it, 2.5 meters away from your frame of reference. Okay, so can you see how your frame of reference, now it has got closer to your frame of reference. So it actually moved towards. Okay. Tell me about the gradient.
It's constant, but it's negative.
It's negative. Okay. The gradient is constant. So we have a constant velocity. Again, constant velocity. What does that negative mean?
Go down. Same direction.
Negative is right. So even though it is now going to the right, because we know it's coming back towards the frame of reference, we can see that the gradient is negative, which means our velocity is negative, which means it has changed direction. Okay, this is going left, This is going right. But can you see that it is still on the left of the frame of reference? So it is still, if you were watching this, imagine yourself here standing, excuse me, and let's say your friend is walking away from you. They are going to be walking away from you, excuse me, at a constant velocity on your left. They then start coming back towards you, and that's where we are. So there was a change in direction, moving away from frame of reference, moving towards frame of reference. Oh, sorry guys, I got a tickle in my throat today. It's terrible. Okay, I want you to try and write now a description. Tell me about the motion, and then I'm going to go through it with you and see if you have hit all the things that you need to pick up. Okay, quickly write a description. I love the way I'm holding my hand up to my mouth. Okay, so what I'm looking for is I would like you to have object, let's just call it an object, a person if you want to say person, object moving at a constant velocity to the left away from frame of reference. Okay, just so that you know the key. From the frame of reference, then moves at a constant velocity to the right towards frame of reference. Make sense? Okay. What could we use the x-axis as? The frame of reference, or the point of reference, or when you say relative to, that would be the point. Okay. All right, let's take a look at Think Tank 1. Oh, I don't know what to put here. Okay, on page 286 to 288. It is clear that I want you to do all of those exercises. Let me just check on the planner what I have planned. Tomorrow is the last day I see you for the week, so I need to do a little task with you tomorrow. So tomorrow I'm going to just quickly give you something very short, so it won't take up the whole hour, just to see if you're realizing how these graphs look. So it will only be a position time graph that I'll give you, and you're going to interpret the motion, okay? Okay, so you can start with it now. You're going to complete it tomorrow. So please start with it now. And I'll give you like the last few minutes of tomorrow's lesson to do the task. Okay, it won't be a long task, and this is your very last task for the term until assessment week. So next week we won't have a task. Okay, luckily we only needed 6 tasks this week. Yeah. Trust me, girls, I didn't enjoy the tasks just as much as you didn't. Setting the tasks are quite a job. Okay, any questions at home? I'm going to stop the recording. Are you guys okay?
Yes, ma'am.
Yes, ma'am.
Okay, I hope